Hello, my name is Nahuel, and I will talk about rank-dependent branching selection particle systems. This is a work in collaboration with Pablo Groisman, and it will be available in arXiv very soon. The model we study is called the Np-Bbm. Bbm is for branching problem motion. It is about a finite set of particles in line, evolving in a Markovian way in continuous time. Particles evolve as independent Brownians, except at times at which the branching selection mechanism occurs, and it is in the family of Brunet-Derrida models. Consider a function b, that is here, that we'll use to decide whether a birth of a particle occurs. Consider also a probability d, that is here, supported on this set here. We'll use the same letter d to refer to both the probability d and its distribution function here. As you can see, it can have mass at minus infinity, that is represented by this gap here. Okay, suppose we have nt particles at time t. What we do is we take the function b, that is this one, and we divide its domain into nt-1 equidistant subintervals. The resulting grid here represents the quantiles of the particles. So the 0 represents the quantile 1, this is the second quantile, and so on until the end of the grid that represents the quantile nt. Okay. So to each quantile, we attach an exponential random variable whose rate is given by the value that b takes in this point. The next step is to make the particles evolve as independent Brownians until the first clock rings, that in this case is the one associated to quantile j. And here's where the probability d appears. Conditioned to the event that the quantile j has run, we divide this unit interval into j minus 1 subintervals. And okay, we draw a random variable that is represented by this cross here with distribution d. So in this picture, we did it using the generalized inverse of this function and a uniform random variable. Okay, and depending on what interval contains this cross, we select another quantile. Let's say that it is the quantile I. Okay, so once this quantile I and this quantile j have been selected, what we do is at this time we make the ith quantile jump on top of this quantile j, and this mechanism creates a drift to the right of the cloud of particles. Another way of thinking this is that the quantile I dies and a new birth is produced in this quantile. So that explains the letters B for birth and D for death in the model. So another comment is that when this random variable is minus infinity, what we are doing is we are picking a particle from an infinite reservoir located at minus infinity. Or in other words, we don't kill any particle. Okay, the first example we show is the standard branching Brownian motion that is obtained by these particular values of E and D. Okay, in the branching Brownian motion, every particle branches at rate 1 into 2. And in the rest of time, they behave as independent Brownians. Other model is the Np-Bbm. In this model, we have n particles, and every particle is a Brownian motion. And at rate 1, every particle branches into 2 also. But when the particle branches, immediately the leftmost particle dies. So the number of particles is conserved. And this model is obtained by these two particular values of B and D. In this reference, it has been proven that this model has has a free boundary problem as scaling limit. Okay, finally, we mentioned this model that has been studied in this paper. And in this model, we have n particles also. And at rate proportional to n, a pair of particles is selected uniformly at random. And the one located to the left jumps on top of the one located to the right. And okay, this model is obtained by taking these two particular values of B and D. And here the authors prove that it has this scaling limit, that is the Fisher-Kolmogorov equation. We have this expected scaling limit for our model. That can be, it can be deduced by the use of heuristic arguments. Here, the lowercase u represents the scale limit of the empirical distribution of the process, and uppercase u represents its cumulative distribution function, and they are everywhere evaluated at t and x. Of course, this equation is consistent with the scaling limit that have been obtained in the literature for particular cases of our model. Let us mention that the techniques used to obtain them vary significantly from model to model. For instance, we expect a connection between the presence of atoms in the death probability with the presence of free boundary in the scaling limit. For that reason, we think that this scaling limit is far from being proved. Okay, here comes our first result, our main result, sorry. We have the BD branchy Brownian motion, starting with n particles. And we assume that both B and D are dominated from below by the function x to the k, here, x to k. We observe that this is a quite mild assumption since x to the k goes to 0, except of course for x equal 1. Okay, the first part of our theorem refers to the case for which the number of particles is conserved, so we don't have mass at minus infinity for probability d. And in this case, the model has an asymptotic velocity that depends only on n and not on its initial distribution. Furthermore, this sequence of velocities converges to square root of 2. In the second part of the theorem, okay, the number of particles grows exponentially. So we are taking this positive mass at minus infinity. Here we have also asymptotic velocity square root of 2. We now introduce a related family of models that we call the Np-Bbm. The parameters are an integer greater than 2, a parameter lambda that is a positive number, and probabilities on the set of pair of integers I and j with I smaller than j and both smaller than k. Okay, what we do is we start with n particles. They evolve as independent Brownians, and at rate lambda n, a k-tuple is chosen uniformly at random, like here, and instantaneously the quantile I among this k-tuple jumps on top of quantile j, as in the picture. For this model, we have this scaling limit. The scaling limit is this Fisher-Kolmogorov equation with this HP that is defined in terms of the parameters of the model. And the case k equal 2 corresponds to the model already mentioned. And also we mentioned that we can tune the parameters of the model in such a way that the function HP, this function, is as close as desired to any continuous function h. In other words, these microscopic models here approximates any Fisher-Kolmogorov equation. Okay, we need also this domination result that says that we can stochastically stochastically compare two BD-BBMs, in this case the red one and the blue one. If the blue functions if the blue functions dominate the red ones, as in this condition, then we can say that the red BBM is dominated by the blue BBM. This means that they can be coupled in such a way that for every time the blue particles dominate the red ones in the mass transport sense. And of course, the domination of the corresponding velocities is inherited from this domination. Okay, we finally give a sketch of the proof of our main result. Recall we have a BD-BBM such that both here, B and D, are between x to the k and 1. Okay, our domination result from the previous slide allows us to dominate the BD-BBM, this one, from above by the standard BBM. Okay, and we know that the asymptotic velocity of the standard BBM is square root of 2. Also using the domination result and due to our hypothesis here, we can bound this model by this BD BBM with this particular B and D. Okay, but this process is very close to a particular Np-Bbm. This particular Np-Bbm is the one that for which the kth minus 1 quantile jumps on top of the kth one with probability 1. Okay, but how we dominate the velocity how we control the velocity of this process? Because we can do it thanks to the fact that we have the scaling limit. And that's all. Okay, I have some conclusions that you can read by pausing the video. And here are the precise references that have been mentioned. Okay, thank you very much.